My name is Jim Hazard. I am not a FLAC2D developer, but I have been working on examples and things like that for the documentation. So I'm going to do my best to guide you through a couple of topics here. And so we got 3 topics today. All right, constitutive model, mathematical simplification of complex material behavior. So as you know, these materials are usually soil or rock, and the micromechanics are complicated and strange. And we are not in any way trying to replicate the physics of the micromechanics. You can play games like that with PFC and some of these particle programs. The whole point of a continuum program is that we don't need to get into that level of detail. And we can assume that these micromechanics are really a continuum with some sort of smeared out behavior. You know what I mean? We're not looking at particle by particle. We're just assuming that that behavior smears out and can be represented by some sort of mathematical function, right? That's basically what the model is. There are many, many, many different constitutive models representing many, many different types of material, and not just in geomechanics. People doing steel and different types of materials. They have their own models. Our models are often pretty common. That's a summary of everything that's on that slide. So it's pretty easy to think about these things in one dimension. So imagine you have stress plotted versus strain, and I'm sure you've seen curves like this before. You start squeezing something, the stress increases. Get to some point where maybe you have failure, stress possibly decreases. So thinking about this in one dimension as a curve is relatively easy and stuff that you've seen probably 100 times before. Stress strain behavior for a one-dimensional compression test. It gets a little more hairy when we start thinking about it in 3D, but as a user, you don't often need to worry about the details of them. So this is some of the terminology that people use, including us. So imagine you have a sample and you start loading it up. It just behaves elastically, right? So for every increment of strain, you get some increment of stress. And that increment depends on the Young's modulus and Poisson's ratio, right? If you unload that, you get back to where you started, right? So the definition of elastic is essentially loading and unloading gets you back to the same place. Eventually, you're going to get to some point where it yields. And then what happens after that is where it gets interesting. So in the world of soils, we often assume that something is perfectly plastic, so it just keeps on deforming, but it maintains the same level of stress, right? In the world of hard rocks, you might have something that's more brittle. So it reaches the peak strength and it basically explodes and goes to some residual strength, right? And then you have properties in between that, right? Where maybe it's something between perfectly plastic and brittle. So it actually loses strength, but doesn't necessarily explode catastrophically. And so you would call this softening, and then it goes down to some residual strength. This is, well, at least in the rock world, this is mostly what we're doing. And then it's also possible to have plastic hardening certain types of soils as well. It reaches the yield point and actually stress continues to increase as you add more. So this is the non-mathematical version of the constitutive model behaviors. And this is just a little plot showing you. I have to apologize here. We're mostly in our office. We're mostly like rock people. So a lot of these things are talking about rocks. I'm guessing most of you are probably soil people. Am I right? Okay. So this is kind of a rock example, but you get the idea. You can imagine if you have a massive rock that's maybe fairly deep, you're going to get this brittle behavior. If you have something that's maybe moderately deep with a bunch of joints in it, you might get some sort of softening behavior. And if you've got something that's more like a soil or some kind of altered rock or some kind of heavily jointed material. Look at this elastic plastic beam. Okay, in FLAC2D, there's 20-something different constitutive models. A lot of them you'll probably never use, but different people require different constitutive models for different projects and different material types. The ones in bold here are the ones that you're probably maybe going to use. The null model, you already saw that, I guess. The tunnel, you can just, in fact, if you're trying to model a tunnel, you can actually just delete the zones and they're gone and you model the tunnel. But you can set the zones to null, which means they basically have no stiffness. And that does exactly the same thing. The only reason you would do that is if you wanted to bring them back again. If you're doing like backfill in a mine, for example. So you null them, everything squeezes, and then you want to bring them back again as backfill. You can do that. So you just change them to null and change it back to something else. If you're never going to bring them back again, you can just delete them and life will be easier. Elastic material is exactly what it says, isotropic elastic. So you give a Young's modulus and a Poisson's ratio, and it just deforms elastically, and it's the same in all same stiffness in all directions. You could have these more wacky elastic models where they have different stiffnesses in different direction. I have seen people use transversely isotropic elastic. So imagine you have a bedded material, so it's stiffer in this direction than it is in this direction, or vice versa. I've seen people do that. I don't think I've ever seen anybody actually use orthotropic elastic, where you might have 3 different stiffnesses. It starts to get complicated. Prager used to be more popular for soils. I haven't seen that in use much recently. Moore Coulomb is a sort of workhorse of constitutive models. Everybody uses it as a kind of starting point. It's relatively simple. It's very intuitive. It's what everybody learns in school. You have cohesion, you have friction. The thing fails, you move on with it. Ubiquitous join I'll talk about later. Strain hardening, strain softening, which is what I was just showing in that graph. You can have things, instead of being perfectly plastic, they get softer, they get harder. Hook brown, if you're a rock person, you know what that is already. Modified cam clay, if you're a soil person, you probably know what that is. Plastic hardening is very popular these days. Yeah, there's a soft soil and a soft soil creep. Interesting. Norsand is getting very popular with tailings dams. For whatever reason, anybody who's doing tailings dams wants to use Norsand. And then actually there's one that's not listed on here, which is our own liquefaction model, P2P sand. And then there's this IMAS model that we use for cave mining, which I'm not going to go into. If you're doing creep modeling, which means you have time-dependent behavior. So what it actually means is you load up a sample to some stress and you hold it, it's still going to deform. So it's kind of a weird thing, right? You're not increasing the strain, you're not applying anything to the boundaries, and yet it continues to deform. So this is the creep behavior. I'm certainly not going to go into that, but there are a whole bunch of models related to creep, give you different types of behaviors depending on the stress state and so on. People use this a lot for salt. You can see the bottom one is actually called something salt. Then this one is related to, so yeah, this one's also related to salt. So anyway, you can imagine salt as a creeping material, right? You just hold it at some stress, and it squashes itself. In FLAC2D and FLAC3D, you also have to specify a constitutive model. The thermal, if you're doing thermal analysis, and the fluid, if you're doing fluid analysis. We're not going to talk about thermal in this course. We are going to talk about fluid. Most of the time, you're running a fluid. Well, all the time, if you're running a fluid analysis, you're either doing isotropic, which means the permeability is the same in all directions, or anisotropic, which means the permeability is not the same in all directions. Those are your only choices for fluid. Have the ability to create your own constitutive models. You can do this. You actually write it in C++ and make a DLL. Pilot, it makes a DLL, and then you just stick it in the right directory. And FLAC2D sucks it in, and you can use that constitutive model as if it was built in. And it's cool because it goes just as fast as the built-in model. Because you compile it as a DLL, plugs into the thing, and just goes as fast as if it was a built-in constitutive model. And the use of it is exactly as if it was a built-in. So it's a little bit of effort. You know, you need to know a little bit of C++ to build these things. It's not a lot of effort because we give you an example. We basically give you more Coulomb. You just want to make modifications to that. You can do it. You recompile it, plug it in, and you're good to go. It sounds advanced. People do this, especially in the soils world. Not so much in the rock world because nobody really knows what rocks behave like anyway. But the soil world, people have very specific models for different soil types. London clay or Boston blue clay or whatever, right? They do build these things. So yeah, that's it. There are also some, not yet for FLAC2D, but hopefully in the near future, some user-defined models on our website that other people have written that you can go and grab and use. So for the old FLAC, there's PM4 sand, UBC sand, 3 or 4 other crazy things that people have written. You go and grab them and plug them into the old FLAC. FLAC2D is relatively new, but the hope is that these things will be also available for FLAC2D in the relatively near future. They just sit on our website as an address.